Good morning, professors. I welcome you all for the fourth day of FTPP. And we have Dr. Alan Joseph, sir. So he's our resource person today. He's here to teach us heap operations and their applications. Welcome, sir.
Thank you, ma'am. Thank you.
You can start the session, sir.
Yes. Yes. Good morning. So I'll start today's session with heap operations, and the next one is going to be my applications with respect to heap. All right. So let me just start. Is my voice audible to everyone? It's like, is it okay? Can just respond in your chat column, or can just tell, is my voice audible? I think it. Ma'am, Aarti ma'am. Yeah, is my voice audible? Just a minute. Yeah. Thank you, Mohan Raj, sir. So we'll just start with today's session. So what I'll do is I'll just directly go into the heap operations. So before that, we'll just see some introduction about heap. All right. And then we'll just try to see heap applications. And in the end, we'll just try to implement a heap sort. Okay. This is one of the application of heap. So let me share my screen first. So I'll just try to share my screen. All right. So yes, is my screen visible to everyone? Is it visible to everyone? I have shared my screen. Is it visible to everyone? Uh, okay, since, yes, thank you, sir. So let me just start with the first one. All right, so I'll just start directly to the heap operations and applications. So let me just start. So let me just go on with the agenda. So this is like a basic heap. We see a heap of sand when we are constructing a house, or you can see this by the side of rivers. All right, so this is basically a heap structure. All right, so let me just start with the agenda. So in the agenda, you will be having introduction to heap data structure, operations, and application. The final one will be applications. So we'll just see these three today. All right, so let me just start with the first one. The first one is introduction to heap data structure. So this is the introduction to heap data structure. So heap data structure is a complete binary tree. So they're telling heap data structure is a complete binary tree. Binary tree means it's like it has a single root node and it has two childs, one on the right and the next one on the left. So this is basically a binary tree. All right. So they're telling heap data structure is a complete binary tree, which means that it will have root node as well as child. All right. So it can have one child also. So this is your a binary tree. So we'll just try to go on further. So in the next thing, we'll just see the heap properties. The properties of heap are max heap property and min heap property. So these are the properties of heap. So we'll be discussing mainly about this kind of heap. All right. So let me just start with the max heap. All right. So the max heap is this. Any given node is always greater than its child nodes or node. It means that when you take a particular node, it has to be greater than the child node. So this is your max heap. As the name implies, it is going to have the maximum value. So it is called a max heap property. And the key of the root node is the largest among all other nodes. They are telling you that the key of the root node is largest among all the nodes. This means that they're telling the value of the root node. The thing is, they're telling the value of the root node is largest among all nodes. Okay, so I'll just freeze the screen for just 1 minute. All right, so let me just freeze it for 1 minute. I'll just come back 1 minute. Okay, so let me just go again the maxi. All right, maxi. All right, so the maxi is like at any given node is always greater than its child node. All right, so it means that at any point, what you'll have is you'll have a node which is going to have greater value than the child node. So this is your uh, maxi property. All right, so I think I'll just show you the next one. All right, so just one moment, please. Yes, thank you. So I'll just go on to this maxi property. At any given node is always smaller than its child node. And so this is min heap property. Any given node is always smaller than the child nodes. And the key is nothing but the value of the root node is the smallest among all other nodes. So this is your basic thing. So let me just try to demonstrate to you how this one works. So this one is a max heap. All right. So this one is max heap. According to max heap, they just say this property, any given node is always greater, which means that you have any given node is always greater than the child node, and the key of the root node, it means that the value of the root node is the largest among all. So let me just display this to you. So we find that this is the root. The top one is the root, and it has to be the maximum, which means that it will hold the maximum value when compared to all the other nodes. So you see that 9 is greater than 5, 1, 3, 4, and 2. So this is your basic one. In the next one, what happens is we just see a 5 here, and 5 is greater than 1 and 3. And the last one, we have a 4 here, and 4 is greater than 2. So this is your maximum heap. We'll just go on with the next one. So the next one is your min heap. So as I said earlier, min at any given node is always smaller than the child node. You have to see this word called smaller. The node will be smaller than the child node, and the key is nothing but the value of the root node is smallest among all nodes. All right, so all other nodes. So we'll just see this by means of this diagram. So we see that this is your root node, and it is having the value of 1. And compared to all the other nodes, this node has the small value. So this is a min heap, which means that the root node has the smallest value. And when you take the other one, so this is your child. So this is going to have your value of 2. So when it is compared with the other two child, it's lower when compared with 4 and 5. So this is your min heap. Similarly, when you compare 3 with 9, 3 is lesser. So this is your min heap. So these are the two properties of heap. So you have max heap and then you have min heap. All right. So we'll just try to go on with heap operation. One of the main operation of heap is called heapify. So you'll use this command in almost, it's not a command, it's like you use this function in almost all languages, be it Python, C++, Java, or whatever it is. You will use this property for writing a heap operation. So let me just start with the heapify. So heapify is the process of creating a heap data structure. Heap is like, as I said earlier, it's like a, a sand sand-like structure. Heap data structure from a binary tree. A binary tree means it has a single root node and it has child. It means that it has a parent and child. All right. So this is your binary tree, and it is used to create min heap or max heap. So according to what we saw earlier, min heap is the value is very small in min heap. It means that the root node will be having a lesser value when compared to all the other nodes. This is your min heap. In max heap, what will happen is you'll be having a root node which is going to have a maximum value. So we saw this in the previous two examples. We'll just try to manipulate this further. All right, let me just start with the next one. So what we are going to do is we're going to start with an array. So as you all know, array is a collection of similar data types. So all these 3, 9, 2, 1, 4, 5 are all integers. So these are all integers. All right. So the data type is similar. 1, 4, 5 is similar. And then what you find is you find 0, 1, 2, 3, 4, 5. So these are the indices. It's called index. All right. Which means that for 3, the index is 0. For 9, the index is 1. And for 5, the index is 5. So when you want to have access to these data, what do you have to do? You have to use some array operation to access it. It means that you open a square bracket and close bracket and give the index and get the value back. So this is your input array. So this is your initial array. So we'll just try to start with the next one. All right. We are going to create a complete binary tree from the array. All right. So I'll tell you what is complete binary tree. So we are having a parent here, which is nothing but a root node, and it has 2 childs. All right. 1, 2. All right. So this one also has a connection with the parent. So this is called the parent of, so 9 is called the parent of 1 and 4, which means that we have an index of 1, which is the parent of 3 and 4. All right. So, and the last one is, you might be wondering why it is called a complete binary tree. Remember, you have a, this one is called the left child. It doesn't have a right child. All right. It doesn't have a right child. Even though it doesn't have a right child, it means that it is a complete binary tree. So the thing is, you can have a single child and a single parent, and the child has to be on the right side, or the child has to be on the left side, and it even have right side. And the next one is, you can have a single parent having 2 nodes, one on the left and another one on the right. Right. So let me just try to tell you what's actually happening here. So I'll just clear all the options. So let me just erase all link of slides. So I'll just go on from the basics. All right. So see, you find here 0. You find the term 0 here. Note this carefully. You find the term 0 here. So I'll try to clean these schemes also. So see, for 0, you have a 3 here. So I'll just go to the next slide. For 0, you have a 3. And in the next one, for 1, you have a 9. So the index of A of 1, suppose let A be the variable assigned to this array, A of 1 is going to have a value 9. So we have a value 9 here. Okay. So, and what the next one? A of 2. A of 2 is going to be having 2. So the index is A of 2, the value is 2. And the next one is A of 3. For A of 3, the value is 1. So we have a 1 here. Similarly, we have the value of A of 4 and A of 5 to be 4 and 5. You can see all these aligned in a systematic way. So this is called a complete binary tree. All right. So let me just start with the next one. So this is a complete binary tree. So let's just go on to the next one. These are the steps to heapify. All right. Listen carefully. You'll be asked to heapify your problem based upon what the data given. So the steps for heapification is this one. So let me just start with the first one. So we have to start from the first index of non-leaf node. So let's just start with the first index of non-leaf node. So you're going to start from the first index of non-leaf. You're not going to use a leaf node. So I'll tell you what is the difference between a leaf and a non-leaf. Even though you know, if you know this, I'll just try to give you an idea of what is a leaf and a non-leaf. So this is called a leaf because it doesn't have any child attached to it. This is also called a leaf. It doesn't have any child attached to it. And the next one is called a leaf. So these three are called leaf nodes because they don't have any attachment. All right. So the next one is this is your non-leaf node because it has two childs attached to it. And this one also is a non-leaf node. It has one child attached to it. And this one is going to be your master. It means that it is the root node and it has two childs attached to it. All right. So this is your non-leaf node. So the non-leaf node in the indexes of non-leaf node are 0, 1, 2. And the values are for 0, it is going to be 3. For 1, it is going to be 9. And for 2, it's going to be equal to 2. So let me just go on with the next one. Start from the first index of the non-leaf node, whose index is given by n by 2 minus 1. So let's just try to work this one out. All right. So this is your non-leaf node. As I said earlier, 2 is a non-leaf node, whereas 1, 4, and 5 is going to be your leaf node. Let me just start with the first one. All right. 2 is a non-leaf node. So how do you work with this one? So with this, use this step. Start from the first index of non-leaf node. So the first index of non-leaf node is this one. So the value is 2. What will happen is the first index of non-leaf node is 2, and they're telling that n by 2 minus 1. All right. So what will be the n? Can anyone tell me what will be n? Yes. So I'll just tell you what is the value of n. N is the number of nodes. So let me just go on with the number of nodes. So you have 1, 2, 3, 4, we have 5 and 6. So we'll take these 6 nodes. The value of n is going to be equal to 6. So we'll take 6 divided by 2 minus 1. All right. So 6 divided by 2 minus 1. So what will be the result? So it's going to be resulting in 3. All right. So we have a 3 here. All right. So if I'm right, yeah, no, like 6 divided by 2 is 3 minus 1. So you result in a 2. All right. So we'll just go on with the step. So I'll try to erase this one. All right. So I'm erasing everything. So the equation is n divided by number of nodes divided by 2 minus 1. So it is going to result in 3 minus 1. It will result in 2. So naturally, we'll be picking this one. All right. You're picking this one, which means that you use the formula n by 2 minus 1. So I have the color is changed here. See, all the others have a normal sky blue color, and this index alone has a navy blue. All right. So we have started the first one. Start from the first non-leaf node. Started the non-leaf node, and the value of the node is 2. So let's just go on the next step. So the next step is second one. Set the current element I as the largest. They are asking us to set the current element. So they are going to assign a variable called I, and this is going to be equivalent to large. All right. So they are asking us to set it as largest. All right. So I'm writing it as I equal to large. So we'll just try to write it further. Set current element I as largest. All right. So this step is over. So we have set the current element, which is nothing but 2, and we are making it as the largest. Then after that, we are going to the third step. The third step we're going to do is the index of left child. So it's called the left child. So this is your left child. All right. And is given by 2i plus 1. So let's just try to solve this one. The index of left child is given by 2i plus 1. So let's just try to manipulate this further. All right, 2i plus 1. So I'll just try to solve this one. 2 into 2. All right, we have a 2 into 2, and this is going to be plus 1. So we have a plus 1. All right. So 2 2s are 4. We have 4 here. 4 plus 1 will result in 5. So we have found out the index of left child. So this is your left child. Remember, always it starts with the left, right? It's a left hand side. This is your left child. Its index is 5. So what will be index of the right hand side? So it will be equivalent to the formula is 2i plus 2. So we'll just try to manipulate this for the 2i plus 2. So this is your 2 into I is 2 plus 2. So 2 2s are 4. 4 plus 2 is going to be equivalent to your 6. So here we don't have a 6, but if you try to use that formula, you will get the right child also. So here you have left child as well as your right child. I think I made myself clear. All right. So if you have doubts, you can ask. You can just raise your hands. And I've done with this diagram. So this is your third step. The index of the left child is given by 2i plus 1, and the right child is given by 2i plus 2. Then we have the fourth step. If the left child is greater than the current element. So what does this mean? So I try to erase this one, all right? If the left child, so this is your left child, is greater than the current element. So the current element is 2. So we are checking whether 5 is greater than 2 or not. So we're just seeing that whether 5 is greater than 2 or not. So what happens? They're telling that greater than current element, set left index as largest. So they're asking us to set this one as the largest. So they're just comparing it and they're just making it as a large one. So I'm just writing as L. So this is your current element, set left index as the largest. Then what they're telling us to do, if the right child, suppose if the right child is greater than the current element, so we don't have a right child here according to a problem right now, but this step is applicable. All right. So the node with the node as the right child. If the right child is greater than the element in the largest, all right, the right child is largest, set right child index as largest. So we're just checking for largest. So this is a operation, all right. So we'll just try to go on the next step. So I'll try to implement a code for swap also, so that you're able to work with swap operations. Then they're telling this swap largest with the current element. They're asking us to do swapping. You get a variable and then process it. So this is what happens here. Yeah, kindly listen here. In the previous problem, we have 2 right over here. So this is your 2, all right. So we'll just try to see this one, all right. So we have 2 present right over here, and your 5 is right over here. So what you'll do is you'll just swap this one if it is greater. So naturally it's greater. So what you do is we'll have this 5 and 2 swap. All right, you perform the swapping operation. All right. So what I will do is I'll just try to implement a simple code for swap after completion of this one. Then we have to repeat steps 3 to asking us to repeat steps 3 to 7. Remember, this is your 7th step, and they're asking us to repeat steps from 3. So they're asking us to repeat it from 3. So we'll just try to manipulate this further. So they're asking us to repeat step 3, 4, 5, 6, and 7. All right, they're asking you to repeat all the steps until the subtree is also heapified. So this is the basic function of heapification. All right, let me just give you a normal example of what you do with swapping. All right, so this is your swapping. Before going into the next one, main algorithm, I'll just try to give you a demo on swapping so that you're able to understand what is actually happening here. All right. Yeah. So as earlier, I'll just go on with Dev C++ as my application. So let me just go on with Dev C++ as my application. All right. So I'll write a simple code, and then at the end, I'll just try to write a very complex code for heap sort. All right. So let me just start with the file. All right. So I hope if the screen is visible to everyone and my voice is audible. If not, kindly inform me. So this is your first step. We just go on with include standard input output.h, and this is your first one. All right. So in order to include printf and scanf statement, we require standard input output.h. And in the next step, what you're going to do is we'll just try to do this process called we'll just start with the main. All right. So we'll just write a main here. All right. So what I'll do is I'll create a function for swap before that, because I'm going to create a function. So let me just use the integer value alone for the data. So this is your int. All right. So I'll write the function as swap. So swap one. All right. So I give it as swap one, and I'm going to get two variables int. So let it have a comma b. All right. So we have two variables called a comma b. So just take a little amount of time. So we'll just try to work this further. We'll just open and close a bracket. And after that, what we'll do is we'll just go on with int. So I'm going to have a comma b here. So I have a a comma b here. So we'll just try to manipulate this further. So I'm missing a hint here. Right. So this is done. So the function, right? Yeah. So in the next step, I'll try to enter the values for a. I'm going to hard code it, which means that I'm not going to get the value from the user. All right. So I'll just give the values as a equivalent to 20, and then I'm going to give b equivalent to 10. So this is a small program. It will allow you to understand heap in a better way. All right. So this is your int a comma b, a equal to 10, b equal to 20. And I'm going to create another variable called temp. All right. So this is your temp. So I created a temp variable. So I'll just try to manipulate this temp. So temp is written. So before that, I'll bring the values of a and print f. So I put before swap. So these are the values of before swap. Before swap. So we have a equivalent to. So this is your a equivalent to. So this is going to be your percentage d and b equivalent to. So I'm going to have a b. So this is your. All right. So I'm going to give the value of a comma b here, and I'll terminate it with a semicolon. So this is my program here. So I'll terminate it with semicolon, and after that, I'll just try to use after swap. All right. So we'll just try to work with after swap. So this is your after swap. So after swap, a equals to percentage d. Okay. So we are done here. And one thing we have to do is we have to call the program swap. So this is your swap here. And I will try to reduce the code such as I'm optimizing it. So I'll just cut this one and right over here. So we'll just type this one as int temp here. So we have a temp here. So temp equivalent to. So I'll remove the temp and the main. So we have a main here. I'll remove the temp here. Temp equivalent to. So in the first step, I'm going to give it as a, and the next one is b a equivalent to b. All right. So I given a equivalent to b and b equivalent to 10. So this is a normal program which everyone will do. All right. So this is your 10 program, but in the forthcoming implementation in Heap, I'll use a pointer to demonstrate this one. All right. So this is for your understanding. This is how a basic temp works. So I'll just try to copy this one and I'll use this one here that I'm making the best out of it before swap, and I'll change this after swap. So this is my after swap. So this is your driver code or main driver code. So I'll just call the swap here. Swap equivalent to swap of a comma b. So I call the function. All right. So I make sure that both return 0. Return 0. So this is my first one, and this is my next one. Return 0. So I'm done with this one. So in the next step, I'll just try to manipulate this further. All right. So let me just files save
Sir, slides are visible, sir.
Okay, ma'am. Thank you. Thank you.
Sir.
Yeah, I'll just go on with this one. All right. I'll just try to delete element from a heap. All right. So this is your delete element from heap. So algorithm for deletion in max heap. So what you're going to do is we are going to check if node to be deleted is a leaf node. So just checking whether the node that has to be deleted is in a leaf. If it is in the leaf, what do? You remove the node directly. Else, what you're going to do is you're going to swap the node to be deleted with the last leaf node. All right. So they're asking us to swap the node to be deleted with the last leaf. And finally, we're going to remove the last node, all right, to be deleted. It means that we're going to remove the node to be deleted. So this is your algorithm. We have heapify the array. So we'll just try to go on with this particular problem. We're going to select the particular element to be deleted, and the element to be deleted is going to be equivalent to 3. So we're going to select 3 for deletion. So this is going to be deleted. So according to our algorithm, we have to swap 3 with 5. All right. So we have swapped 3 with 5. And after that, what happens? After this, we just remove the last element. So it's depicted in red color here. You remove the last element. So this is your algorithm for deletion. And finally, what do? You just heapify the array, which means that you rearrange it according to the algorithm which was set earlier for heapify. All right. So we have the maximum element of the root, and all the others will be less than the root. So this is your deletion. So we'll just go on with min heap. For min heap, the above algorithm is modified so that the child nodes are greater than the current node. So it means that the child nodes has to be greater and the current node has to be very small. So this is your operation. And the next one is peak operation returns the maximum element from the max heap. All right. So we have a function called peak, which will get the maximum element from the max heap and or minimum element from the min heap without deleting the node. You don't have to delete a node in peak. All right. So we have completed some of the heap operations, and the next one is we're going to see about heap data structure applications. All right. So these are the following applications. So this is like heap is used while implementing a priority queue. All right. So it's like you just have some interruptions in between. And the last one is you use a Dijkstra algorithm, which means that it is like a shortest path finding algorithm. And for our application, we're going to take this heap sort and we're going to implement it. All right. So you'll just see how this works. All right. So this is going to be our next step. So let me just try to go on with the demonstration. All right. I hope my screen is visible to everyone. And I'll just try to go on. All right. So please note carefully. I'll just try to give another, I'll just try to add some comments so that you're able to see the code in a better way. All right. So by writing it also will be very easier for you. So at this start the first one. All right. So there are many functions. Before that, I'll just start with the first one. Hash include. So I'll include a standard input output.h. So I started with the standard input output.h. So the next one is I'm going to write a function. So let me just. So I'm going to write a function for swapping. Function to swap position of two elements. So I'm going to write like this. Then afterwards, what I'll do is I'll just try to conclude this comment. So let me just conclude this comment, and I'm going to start with the function. So I'm going to start with swap. So void. So void is not supported here, but I'll try to write this one void. Let me check whether it is working or not. If not, I'll just change it. So void swap. It means the function is not going to return anything. And remember, I'm going to use pointers here. All right, this pointer is like I'm going to use a int star a and int star b, which means that I'm going to change the position. All right. So after that, let me just try to create option like this int. So this is my int equivalent to. So this is my int, and I'm going to create a variable called temp. So I have a temp here, and after temp, I'll just try to use star a. All right. So I'm using the star, which is basically a dereferencing operator. Then, so this is entirely different from. So this is your star a. This is going to be equivalent to star b. So this is my star b, and afterwards I'm going to replace it with star b. I think some of you will know how this one works, right? So this is like a pointer. All right. So I'm just using dereferencing operator. So this function is complete. So it's basically a swap. All right. So the next one is we're going to write the function for heapify. So heapify is basically a sorting algorithm. All right. We'll just try to sort this one. So I'll just try to use this one to heapify. All right. So this command to heapify. I think I'm right. Yeah. Heapify a subtree. So it means that you're going to take the leaf mainly. So subtree. So we have a subtree. All right. Subtree rooted. We are going to write it as rooted with node. This is your node. So can you note this line rooted? I'm using the word rooted with node, and this is your I. All right. So this is your I. As you all know, I is the current element, which is an index of. So this is your index in. So I'll try to go down ARR. So this is your ARR. So I'm going to create an array. All right, such that I'll be able to work with the code. All right. So what I'm going to do is I'm going to write the problem like this. This is your ARR. All right. So I've written it like this. So to heapify the subtree rooted with the node I, which is an index, in. All right. So this is your index in ARR of. So I'll stop this here and I'll try to complete the problem. All right. So ARR, I'll just use 2 R's, not 3 R's. So I'll add one more thing. And the next thing is n is the, see, these are all comments, okay? N is the size of the heap. So this is your size of heap. So let's just try to manage this further. All right, so I've given some comments. I'm going to start the function void. So I'm going to give it as void. It doesn't return anything. So we'll just try to go on with void. So we'll just write it as heapify. All right, heapify. And I'm going to pass the array here, int. So let me just pass an array here, ARR. So I'm passing an array. And the other thing that I'm going to give is to this function is the size of the array, int n. And the next one is I'm going to give the current element, int I. All right. So this is your current element index. So we'll just try to go on with the next one. So in the next one, what I'm going to do is I'm going to start the function. All right. Let me just start the function. And before that, I'll try to add a comment here. So let me just add a comment. Find the largest. So this is your max heap, all right? This is your largest. Find the largest among, I'm going to find the largest among root left. This is my left child. So I'm going to start with the left child and then I'm going to end with the right child, all right? It's always left heap. So this is your right child, all right? So I've written it as right child. So I think I'm done here, all right? So this is my command here. So I'll just close this comment and after that, I'll just try to give one more comment. Initialize. So this is one of the basic things of heap sort. So we have an initialize. So I have an initialize largest as root. So we have this largest as root. So we are done with this one. So let me just start with the code. All right. So int. So I'm going to write like this: int largest. Int largest is going to be equivalent to I. So this is my int largest is going to be equivalent to I. So according to our code, we are starting this algorithm. All right. So int largest is equivalent to I, and then we are going to use the formula which we saw earlier. Left plus one. All right. So this is your left, and right. What will be your right? So we'll just right, and right will be equivalent to. So this will be equivalent to 2 star I. 2 star I plus 2. So this is your right. All right. So we'll just have this left and right, and we'll just try to implement this in terms of code. So I'll write it as int left. So this is my int left. So this is my int left. All right. So int left is going to be equivalent to. So according to the formula, 2 star I, we have a plus 1. All right. So this is our int left. All right. So we are done with this one. And after this, we will write this int right. All right. So int right. We can write it in a single line, but for your understanding, I'm just splitting it up into left and right. All right. So I'll just go with left and right, and then 2 star I plus 2. So this is my next one. All right. So I'm done with this one. Left and right. Then afterwards, what do you do? Basically, you have your left and right, then check whether the element that you've taken is largest or not. So we'll just add a comment here. If left child, if the child is larger than root. So I'm going to write here larger than root. It's always good that you comment your code, all right? Larger than, such that when you come back, you are understanding what it is. All right. So this is your larger than root. So what you do is, if left is larger than root, then what you do? You just swap it. All right. So this is the basic thing which happens. So what you do is, we'll check if, in our case, left less than n. So we are just seeing whether left is less than n, where n is the size, and we're using a logical operator here, which is and here, and ARR of. So we'll just see is this left, and then we're going to check whether it is greater than largest. All right. So we'll just name it as ARR of largest. So we have this largest here. All right. So this is if left less than n, which means that you should not run out of nodes. That's the reason that you give left less than n. N is the total number of nodes. All right. So we'll just name it as left. This is your left, and is like this largest. So this is your largest left. I put the name here. So for the next one, all right. So in this case, we have the right side. All right. So we just go on with the right side. If right, if right child is larger, already right side is larger, all right, than the largest and largest. So right, so we'll just see what to write here. We'll use the same one instead of left. We'll just try to use with the right. All right. So I'll just take this code and use it here. All right. So let me just use it here. So instead of left, all I have to do is I have to write right. All right. Right is so here also I have to change it as right. Done with right. almost done. And after, what we have to do is swap. All right. Swap is your program here. Swap and continue. So this is your function. We have swap and continue. So let's just try. All right. It means that I'll write a command for swapping here. If largest. This is my largest. If largest not equivalent to I. So if the current element, as you all know, I is the current element. So we'll just try to work with if largest not equivalent to I. So we'll just swap it. All right. Let's just swap this one. So swap is like you have your pointers here. So let me just write this pointer variable here. So I'll just give the address of the array, ARR of. So I'm going to give the address of the array. Still now I'm not declared the array. So I'll just go through this program again so that you get a better idea of what is actually happening here. So I'm going to take these two values alone and ARR of. So this is my next one. So ARR of largest. All right. So this is your largest. So we have a swap program here. And the thing is, you have to do it recursively, which means that you should call the APP function again and again. So we'll just try to make sure that you call the function again and again. All right. So what we'll do is we just have the heap file over here. Right. So let me just go on here. So we have a heap file. So this is my heap file. All right. Heap file. So I'll pass the array ARR. So after that, I have to send the number of nodes, and finally, I just go on with the largest. All right. So this is your largest. All right. So I'm almost done with heap file. So I've closed it appropriately. Then this is the main function for heap sort. It's like it's not the actual driver code. This is the main function for heap sort. So let me just write it as main function to do heap sort. This is my main function to do heap sort. So let me just write it again. Void heap sort. So I'll use a camel case. Heap sort. So this is my heap sort. And I'll just try to enter only limited number of parameters here. The first one is I'm going to int. This is my int ARR. So this is my int ARR. So I'm done here. Then int n. So this is my int n. So the number of nodes. All right. So we did a max. All right. So let's just try to build a max here. Build a max heap. So this is my max heap. So I have max heap here. All right. So what I'll do is use for loops for getting my data. So let me just start with this one. All right. So for, I'll write like this for. So I'll try to declare it right over here int I equivalent to n by 2. This is my max heap n by 2 minus 1. I think all of you know what is this, the current element, right? I is the current element. And then what you're going to do is if I is greater than, so you're checking whether it is greater than or equivalent to 0. So we're starting from the root node and then we'll just try to decrement it. All right. I minus minus. So this is my for loop. So I'll call the EP5 here. This is my EP5. So it's quite a big program, but like when you try to work it, it's like very easy for you to understand how this one works. All right. So this is your EP5. So I have my EP5 here. And I'm done with this one. And before that, yes, yeah, I'll go with heap sort. All right, so this is a heap sort. So we have heap sort here. So let me just type the code again for int I equivalent to n minus 1. So please calculate this one. Like it allows you to surf through the heap. All right, this is I equal to n minus 1, I greater than 0. So we have a I greater than 0, and the next one is decrement I. We'll start from the highest and then go to the lowest. All right, so this is the next one. So we'll just try to do this, and we'll use a swap here. Swap, and I'll try to pass the element to the array. ARR of 0. So this is my 0. So I have a 0. After that, I have ARR of I going to perform heapify operation. So I just write a comment here so that it is easier for you to understand. Heapify. This is your heapify root element. Root element. So we have a heapify root element to get the highest. So this is your highest. So this is your highest. All right. So we have a highest here. Highest element at root again. So this is your highest element at root. So function again. I'll use a function for printing. So this is your print your data. So we have a print your data. So this is my ultimate function. So we just go on with void print array. We have this void print array. Then int here 0. We'll initializing I into 0. So in some cases, this declaration might not work. So it means that you have to work it again, right? N. So this is your I less than n. And the last one is we have I plus plus. All right. This is the next one. So we use printf statements. So I put percentage %d for my purpose. Percentage %d, and I'll use ARR of I. All right. So I'm going to print the value of the array. I'll put a semicolon here, and the next printf is for new line. Printf. So I'm having the new line. All right. So I'll use an escape sequence called \n, and I'll close this one. And the last one, I'm going to write the driver code. So this is your driver code. Driver code is like this is the function that calls everything. So it's called the main also. This is my driver code. All right, we have a driver code here. So I'll just try to complete this one. Int main. So let me just complete this one. Int main. We have a main here, right? So I'm going to . code the data because I'm not going to ask the user to enter the value. So I'll just hard code the data. All right. So I'll just try to use int. So this open and close bracket. So this is my ARR. So we'll just use single brackets. I'm going to enter the value here. All right. So 12, 11. So let me just use some random values. 12, 11, 13, 5, 6. This is my value. The last set. So int n. So this is my next one. Int n. It's basically the number of nodes, right? So we'll just use size of so this is my size of operator. So we'll just use ARR utility as a size because in the memory cell it will take the entire space, and if you take the single element and then try to work it out, so it will give the number of nodes. So ARR of 0. So this is the next one. All right. So we're almost done. This is area 0 and enter symbol here, and I'll call function heap sort. So this is my sort ARR command. So this is my ARR command. So finally, I have two more lines. No, two more lines are printing, right? So we just printf. So this is my printf. So we have printf here. So we just try to work with this sorted array. So sorted array. All right. So this is your sorted array. So I'll just close this one, and I'll try to use the statement. I'll introduce a new line here. All right. So I'll stop with the last two lines. I last two lines. So we'll just try to execute it and check for errors. Small. So let me just run the program. Yeah. I'll save this one. And this one and this heap swap one. This one helps. Next thing is to rectify almost all the errors. So it's not in have in all the equations because most no, yeah. Then if I'm define is lose a semicolon. So we'll just try to compile this. And swap makes
Professors, kindly wait. The resource person has some network issues. He'll be joining soon.
Ma'am, are you able to hear my voice right?
Yeah, you're audible, sir.
Okay, okay, ma'am. So
Alan,
this
sir,
is my
you're
last
audible.
2 minutes. Yes, ma'am. Thank you. So I just have 2 more minutes. So the thing is, I just wanted to run this program. I'm almost done with the main. All right, the main I just hard coded the program. So int ARF 12, 11, 13, 7, 5, 5, 6, 7. So this is your data. All right. So I've called for the number of nodes. You take the whole array and then divide it by one single element size and result in the total number of nodes. And we call the heap sort here. And afterwards, we'll just try to print the array. So we'll just try to compile this. So I'll compile this one. And finally, it's having 0 errors and 0 warnings. And I'll just try to run this one. And I obtain my result. So the result is like it has been sorted. So we'll just go on with the plus here. So I'll magnify this. This is your final result. All right. So we have 5, 6, 7, 11, and 13 after implementing this heap sort. So this concludes the implementation of heap sort. And I've given you the basic operations of heap. All right. So if there are any doubts, you can just ask me right now with respect to the heap. All right. So just try to minimize this one. And I didn't share my screen. Just one. Yeah, this one. I didn't share my screen. So I'll just, so this is your main function, and you have int ARR, the entire array details, and then we are going to take the number of nodes, and we are going to use the heap sort function, which we wrote earlier. And finally, we are going to print the data. So on printing, you just see this one. All right. So this is your final data. So we'll just try to compile this. All right. So execute compile, and I'll run this program. And you can see the difference between the result and the actual code. 12, 11, 13, 5, 6 is your input. And your sorted array is like something like this: 5, 6, 7, 11, and 12. So this is your sorted array. So this is your heap sort algorithm. And yeah, that's it. I'm concluding it. So if you have any doubts, you are free to ask. Thank you.
Thank you so much, sir. Participants, if you have any doubts, please do post in chat box, or you can unmute and ask the question. So thank you, participants. Sir, can you turn on the camera so that we can take a photo? Participants, please do turn on your camera for a photo session. Participants are requested to turn on the camera for photo. Please turn on your camera. Thank you, participants. You can join after 15 minutes. Thank you, sir.